Hello everyone. General rules of probability. This is the chapter 13 of our textbook. Random phenomena. Unable to predict the outcomes, but in the long run, the outcomes exhibit statistical regularity. We talk about events. So, what is a random event? An event is considered random if we know what outcomes could happen, but not which particular values will happen, like tossing a coin and rolling a die. Venn diagram. This is a Venn diagram. Rectangle represent the sample space S. Circle represent an event E. Union. Let A and B be two events. Then the union of A and B is the event defined by A union B equal X. X belongs to A or X belongs to B. Yes, A or B. So this is the Venn diagram to show A union B. So this area is the only A area. It does not belong to B. This one only B area. It does not belong to A. Intersection. Let A and B be two events. Then the intersection of A and B is the event defined by A intersection B equal X. X belongs to A and X belongs to B. Here A and B, but union it was A or B. So that is the difference. So this is a Venn diagram for A intersection B. Then complement. Let A be any event. Then the complement of A defined by A bar equal X. X does not belongs to A. So this is the Venn diagram to show A complement. You see A circle. So outside of the A is the A complement. We use these three notations to show A complement. Then example. Let S equals 0 to 6 and A equals 0 to 4, B equals 3, 4, 5. So all elements of A are in S and all elements of B are in S. Therefore, A and B are events of S. How do we use this information for a Venn diagram? Yes, first consider the common element of A and B. Are there any common elements of A and B? Yes, 3 and 4. Therefore, 3 and 4 should be in this region. Then go to the A. So consider A elements 0, 1, 2, 3, 4. But you see 3 and 4 is already in A. Therefore we need 0, 1, 2. It is in the region only A. And similarly B, we have 3, 4 already. Therefore the last number 5, it is in the region only B. So now go back to the sample space. So what are the numbers of the sample space? 0 to 6. So we already have numbers from 0 to 5, but 6 is not in S yet. So X6 should be outside of the two circles. Right, then not A. A complement is equal 5, 6. You see elements of A is 0, 1, 2, 3, 4 and consider the sample space. So you have 5 and 6. Therefore, A complement is 5, 6. Then B complement. Again, 3, 4, 5 are the elements of B. So we have 0, 1, 2, 6. Therefore, out of the B. Therefore, B complement is 0, 1, 2, 6. A or B. you see A union B, all elements of A or B. So you see A 0, 1, 2, 3, 4 and B also 3, 4 and 5. But we already have 3, 4 in the set A union B. Therefore, we should write 5. Then A and B is 3, 4, not A and B. It means A intersection B complement. So first understand the A intersection B. What are the elements of A intersection B? 3, 4. Then find the complement of that. What are the other elements we left? 0, 1, 2, 5, 6. So that is the A intersection B complement. In problems, you will recognize that you are working with union if you see the word or, intersection if you see the word and, complement if you see the word not. Then mutually exclusive. Two events A and B are called mutually exclusive if intersection of A and B is empty. So how do we show this using a Venn diagram? This, you see we don't have a common element or common region of A and B. Is disjoint. They are disjoint. They have no outcomes in common. They can't occur at the same time. The outcome of the random experiment cannot belong to both A and B. Next one is independence. Two events A and B are independent if knowing that one occurs does not change the probability that the other occurs. So how do we check the independence? Two events A and B are called independent if probability of A intersection B equal probability of A times probability of B. Actually, if this equation is satisfied, then we can say those two sets are independent. Note, if A and B are disjoint, which means mutually exclusive, then probability A intersection B equals 0. Now you see the difference between independent and disjoint. The general addition rule. For any two events A and B, we can write down probability A union B, or we can say probability A or B equal probability of A plus probability of B minus probability of A and B. Note, if A and B are disjoint, it means mutually exclusive, then probability A intersection B equals 0. We know that. Therefore, this equation becomes probability A union B equal probability of A plus probability of B. Why? Again, if A and B are disjoint, then intersection probability of intersection is 0. Logic. So A union B, when probability of A is added to probability of B, the outcome in A intersection B are counted twice. Hence, probability of A union B equal, see, probability of A, it means whole A, right? Then probability of B, whole B. Now you see we add 2 times A intersection B. Therefore, we should subtract 1 A intersection B. Then you can have probability of A union B. Example. At the entrance to a casino, there are two slot machines. Machine A is programmed so that in the long run it will produce a winner in 10% of the plays. Machine B is programmed so that in the long run it will produce a winner in 15% of the plays. If we play each machine once, what is the probability that we will win on both plays? Okay, let me explain this first. So here you should understand machines are independent. So first let me define events. I use A be the event that we win when we play machine A. Then probability of A equal zero point 0.1 because 10%. Similarly, machine B, probability of B equal 0.15 because 15% winner. Then we will win on both plays. It means probability A winner and also B winner. Therefore, probability of A and B. Probability of A and B equal. You can use probability of A plus probability of B minus probability of A union B. But here we know um, we know these machines. Two machines are independent. Therefore, you can use probability of A and B equal probability of A times probability of B. Then multiply these probabilities. It is 0.015. Then go to second question. If we play each machine once, what is the probability that we will lose on both plays? Alright. So what that mean? It mean probability not A and not B. Why? A is the winner. You know, uh, A be the event that we win when we play machine. Therefore, lose mean not A. But both lose, it means not A and not B. Then probability of not A and probability of not B. Sorry, probability of not A and not B. So this equal. Now you know machines A and B are independent. Therefore, we use probability of A and B equal probability of A times probability of B. Similarly, this complement also independent. Therefore, we can use 1 minus probability of A, which is complement. 1 minus probability of A is what? Probability of A complement. Similarly, 1 minus probability of B, that means probability of B complement. Then you can multiply, answer is 0.765. If we play each machine once, what is the probability that we will win on at least one play? At least one play. What is the meaning of at least one play? It means maybe one can win or both can win, right? Maybe yes, one or both. Therefore, what that mean? In this case, we are trying to find probability A or B. So how do we find the probability of A or B? Use this equation. Probability A or B equal probability of A plus probability of B minus probability of A intersection B. But we know A and B are independent. Therefore, we can use probability of A and B equal probability of A times probability of B. Now we can write this equation, modify this equation according to these conditions. Probability of A or B equal probability of A plus probability of B minus probability of A times probability of B. Now we know this probability, just plug the numbers, then you can get the answer 0.235. Yes, here actually we assume or we know machines are independent. That's why we use probability of A and B equal probability of A times probability of B. Similarly, understand probability of A complement and B complement. Please write down on the paper probability of A complement and B complement equal probability of A complement times probability of B complement. Then probability of A complement is what? Probability of A complement equal 1 minus probability of A. That is the solution number 2. 1 minus probability of A. And then probability of B complement is equal 1 minus probability of B. So understand that part. That is very important. Example 2. In a certain residential suburb, 60% of all households get internet service from the local cable company. 80% get television service from that company. And 50% get both services from that company. If a household is randomly selected, what is the probability that it gets at least one of these two services from the company? At least one of these two services. Let me discuss this. Okay, first, let me define events. I say A gets internet service, B gets TV service. So once we define this way, we can write the probabilities of this. What are the probabilities we have? 60%. What is the 60%? 60% of household get internet service. Therefore, probability of A equal zero point 0.6. Then what is the probability of B? 80% get television. Probability of B equal 0.8. Okay, now we have 50%. What is the 50%? 50% get both services. It means probability of A and B. So these are the information we have. Now we are looking for probability subscribes to at least one of the two services. At least one, maybe two. Because we have only two services. Therefore, at least one. Therefore, what is the notation or in probability notation? Yes, this is the case. Probability subscribes to at least one of the two event services equal probability A or B. So probability of A or B equal probability A plus probability B minus probability A and B. Yes, that should be probability A plus probability B. You see it is bracket not closed, but it should be closed. Minus probability A and B. So this equal 0.9. So if I draw this, you see that here by notations, also you see 0.1 is the only A, 0.3 is only B, 0.5 is the both. Therefore, at least one mean 0.1 plus 0.5 plus 0.3. So then second one, exactly 1. What is the exactly? See, second, what is the probability that it gets exactly one of this service? What exactly one mean maybe only internet service or only television service, right? Yes. Therefore, only A is 0.1 and only B is 0.3. Therefore, 0.1 plus 0.3 equal 0.4. That is the only mean actually exactly one service, one of these service. Next, go to the conditional probability. The probability that B occurs given that A occurs is called the conditional probability of B given A. Suppose that we are interested in computing the probability of event A and we have been told event B has occurred. Then the conditional probability of A given B is defined to be probability of A given B equal probability of A intersection B over probability of B if probability of B not equal 0. It is clear. Its denominator can't be 0. Example. For a specific married couple, the probability that the husband watched a movie is 80%. The probability that his wife watched the movie is 65%, while the probability that they both watched the movie is 60%. If the husband is watching the movie, what is the probability that his wife is also watching the movie? Okay, let me discuss this. Before I go with information, just let me define true events and probabilities of those events. You see, I say B equal the event that the husband watched the movie, then A is the event his wife watched the movie. Then what is the probability of B? You see, it is the 80%, therefore 0.8. And probability of A, it is a 65%, therefore 0.65. Then both watch the movie mean probability of A and B. It is probability of A and B equal zero point 0.6. Then what is the question they are asking? If the husband is watching the movie, and now we already know husband is watching a movie, right? So therefore, that is the condition. We already know that. Again, if the husband is watching the movie, okay, now we know husband already is watching the movie, then what is the probability that his wife is also watching the movie? Think this way. Suppose you don't have the first sentence with if, start from if. Then what is the question? What is the probability that his wife is watching the movie, right? If you had that sentence only, you will find the probability of A. Then you have another sentence with if. Therefore, that should be the condition. Therefore, this should be probability of A given B according to the equation. Probability A and B divided by probability of B. Then uh, plug the numbers. Then you will get the 0.75. Yes, it's a high probability. So, independence again. Now, we talk about this first. Two events A and B are called independent if intersection probability of A intersection B equal probability of A times probability of B. So hence we can use the conditional probability of B given A equal probability of A and B divided by probability of A, because again according to this note probability of A intersection B can be written probability of A times probability of B. Why? A and B are independent. We can use that only A and B are independent. So probability of A times probability of B divided by probability of A. Therefore, probability of A cancel. Then you cancel out. You have only probability of B. So probability of B given A equal probability of B if A and B are independent. Thus, in the case of independence, the conditional probability of an event is not affected by the knowledge of the other event. Alright. Difference between independence and mutually exclusive. Actually, I explained this before too, but understand this is very important. Two mutually exclusive events are independent only in the special case where probability of A equals 0 and probability of B equals 0. Also, probability of A intersection B equals 0. So, this is the case. Mutually exclusive events are highly dependent otherwise. A and B cannot occur simultaneously. If one event occurs, the other event does not occur. Okay, now tree diagram. What is the tree diagram? Probability models often have several stages, with probabilities at each stage conditional on the outcomes of earlier stage. These models require us to combine several of the basic rules into a more elaborate calculation. Okay, tree diagram for the experiment of tossing a fair coin twice. Okay, now think about this experiment. We first toss a coin and we check the output. It should be head or tail. Then we go to the second time. Okay, first think about only first time. So this should be this. Stage 1. Toss coin first time. Then next time, okay, you see first time you have H, so second time can be H and T. Or first time you have T, second time can be T and H and T. Therefore, this is the tree diagram for this experiment. You see stage 1 and stage 2 toss coin first time and second time. Then you can write the outcomes HH, HT, TH, TT. So I will explain about tree diagrams more deeper in my next video when I explain the examples. So I hope to explain more examples in my next video. Thank you so much for watching this video.